Good afternoon, everybody, and thank you for attending today's webinar with our ETN member, Crosstown H2R. Today we have a specific webinar entitled Revolutionizing Gas Turbine Combustion, where Crosstown will present its own fuel-flexible, low-emission burner solution for Frame 5 and Avon machines. Today we have Prith Harasgama, co-CEO and also founder of Crosstown, Khawar Syed, CTO, and Franklin Genin, who is head of combustion and senior engineer at Crosstown. Before giving the floor to Crosstown, I would, on behalf of ETN, thank Crosstown for organizing also this webinar, which we feel will provide additional value to our community and to the commitment also of your own organization towards low carbon solutions for the future. With this, I am happy to give the floor to Crosstown. Thank you.
Good afternoon, everybody. Thank you for being here and taking the time to listen to us. ETN, Antonio and Nicolo, thank you very much for organizing this. Really appreciate that. What I'd like to say is, when we started off on this journey to do this new type of combustion burner, which we call the H2R, and that's a registered trademark now, we dubbed it the clean air solution because we're looking for clean air solutions, low NOx and low CO2 using low carbon fuels. And that's the whole framework of how we started this rather long and, let's say, exciting journey. When we set this up, maybe Khawar, you could move to the next slide and give an overview. So we'll give you an overview of the whole way we did this. And again, if you go to the next slide, what we've done is develop a combustion burner for gas turbine asset life extension. There's a lot of machines out there which are older machine, and what this burner does, it future-proofs your GT. It delivers low NOx with both hydrogen and natural gas below 15 ppm and hydrogen below 25 ppm, and operates with any blend between 0 hydrogen all the way up to 100% hydrogen, and it does so seamlessly. So continuously from 100% natural gas all the way to 100% hydrogen, very, very smoothly. And when we spoke to our clients, and in my past life, I did a lot of retrofits while I was with ABB and Alstom. You need to talk to the client, and we talked to them and they said, hey, this has got to fit the current system. It's got to fit into the enclosure or fit into the cubicle. It's got to be easy to retrofit, and all these critical information we received from our clients. And based on that, we developed the burner and then went on to do a customization for the Frame 5 and a customization for the Avon. If we go to the next slide now, this gives you a little bit of background as to where we're coming from. As I said, my background is also in the heavy duty and also aircraft engines at Rolls-Royce. And Khawar here has worked also for Siemens, as well as ABB, Alstom, and Frank and GE, of course. And Franklin behind me has also worked for all of these companies, including MAN Turbo on their hydrogen system. So we have a large amount of experience in the base, and I'm giving you this so we don't have to go through an introduction for every person. And what it shows here is a movement from a smaller machine, 50 megawatts or thereabouts, up to a 540 megawatt machine. And the people sitting in this room were responsible for the combustion systems for all of those machines, including the Siemens Sweden machines, SGT 600 and 800, where the combustion system was developed here in Baden, And then there are other machines that came on later, as you can see. And so we've got a good mix between ABB, Alstom, Siemens, and GE. As you can see here, you've got the NOx reduction over the years. And in 2070, we had NOx reduction with wet operation. And after that, we went to dry operation, and we went all the way down to below 10 ppm with our Crosstown H2R burner. So that's giving you, in a nutshell, our background. Everybody is from an OEM, and as you can see, we're from all the different OEMs, except perhaps Mitsubishi. And I will now transfer to Khawar to take over the rest of the story.
Hey, thanks so much, Prith. And good afternoon, everybody. During the subsequent part of this presentation, I'll firstly go through a little bit about the basics of the H2R burner and how we developed it, and then move on to then the two applications of it, one the Frame 5 and the second the Avon. As Prith has already eloquently stated, we identified certain needs that we wanted to cater for from the client base, and there were a lot of discussions that went behind it. Prith mentioned some quite important considerations. We effectively wanted to ensure that the amount of gas turbines that are out there, there's a vast array of gas turbines. We want to give them a cost-effective life extension. And for the future, this is heavily dependent upon the emissions, reducing emissions regulations, tackling the NOx, as well as the requirement to decarbonize. In order to achieve those, we also then need a technology which has a wide fuel flexibility. That is clear, especially, for example, during the transition from fossil-based fuels to decarbonized fuels, whatever that decarbonized fuel may be. Hydrogen, for example, that it has very different characteristics to natural gas. We've got to be able to cater for those changes. The other thing is that the system must be stable in operation, not only across the engine loads and ambient and the things that we're used to, but also across a wide fuel composition. Those were the critical needs that we then put behind the solution that we came up, which is then the H2R burner. Here you see a depiction of one of our designs. In order to cater for these needs, because there are many types of gas turbines which are out there, the system must be scalable and adaptable. That is at the heart of the system we've developed. It's also got to have multi-fuel capability. For example, a low carbon fuel and natural gas, or blends thereof. The technology we've therefore defined, we say is revolutionary. It is zero carbon capable. It can do, for example, 100% hydrogen, and therefore it fulfills your net zero commitments in the future. We have patented the technology, which is with a patent granted in March of 2025. Therefore, in summary, the product that we have is low emissions, is multi-platform, fuel flexible, and is able to meet future emissions regulations and goals. This slide here shows a little bit about the basics of the technology. Firstly, it's a multi-cluster tubular burner. There are other such burners out there in the field. We picked this type of technology because of adaptability. Let me just explain some of these schematics that we've got at the top here. These pictures here show features of the burner when we look from the combustor up into the burner. So we're looking from downstream into the burner itself, and you see that the burner comprises a cluster of mini tubes. Each tube, you can say, is a kernel of a burner. It's a premixer. What we can do is we can cluster those little premixed kernels into an array of different designs. Therefore, it is scalable and adaptable. Smaller burners that we might be replacing may have fewer tubes. A larger burner that we might replace may have larger tubes. All of them, the design behind that is based around the scaling and design guidelines that we've worked out during the program. And also here, you see hexagonal burners. That's very much applicable to a lot of silo machines. Here we've got a burner which is actually round, also suitable to other machines. That's the adaptability. It also has separate fuel feeds. So, for example, we have in this picture here, we've got our tubes, which are these circles. The dots in the middle are, in this case, piloting. So the system operates with two fuel stages, can be a pilot and a main. It also has the feature, because this is an additively made part, which incidentally also makes it scalable and adaptable, we also have multi-chambers within here, which can allow staging of the pre-mixed parts. This picture here, which is a cross-section through a burner, now we're saying that the combustor is down here. This is the pre-burner plenum up here. These are the tubes. Here are a couple of fuel cleaner, from which we inject fuel into the tubes. Also, because of certain applications that we also want to address, we've made it possible that we can include oil lances and water injection, if water injection is still required for power augmentation, for example, as well as spark plugs. So the burner is adaptable for that if necessary. Also, at the back end, we can configure that for whatever the particular application requires. And that's what we call customized fuel inlet configuration. This slide here shows a little bit about our development through the years. So we developed the system based on a lot of analytical and detailed numerics, but also crucially a lot of atmospheric testing. And through that testing, we've gone through several generations of the burner, where we then verified certain things, such as our scaling laws. Here you see a small burner, here you see a larger burner, as well as different piloting configurations. So we've used it to tailor the functionality of the burner, but also crucially, we've linked the manufacturability with the functionality. So all of these burners are therefore going along a journey where the features that we have incorporated into the burner to give us the functionality of operationability and fuel flexibility have also been aligned with the manufacturing process. They can be effectively manufactured. And just a nice couple of graphics on the left here is a couple of photos taken from the atmospheric rig. This is a picture of the atmospheric rig with the combustor sitting here. So here you see a glass combustor. That's based at the Fachhochschule, Northwest Switzerland, which is sitting close to us here in Baden. But here are a couple of pictures, one showing a burner operating on hydrogen, and the other showing a burner operating on natural gas. And that was part of the process for us then to ensure smooth variability across these different fuel compositions from 0 to 100% hydrogen. After we've gone through this analytical, numerical, and atmospheric testing, it was therefore critical that we took it to the next step, which was then to prove the technology at high pressure conditions. For that, we incorporated a burner into a combustor, which is also an engine representative configuration, so a DLE type of configuration, which we integrated into a test cell at the Cesta Labs in North Italy. We tested that burner from 100% natural gas to 100% hydrogen, and we monitored all of the critical parameters to us: emissions, also operability, and also things such as metal temperatures, which are crucial for durability, as well as dynamics, combustion dynamics. So basically what we've done through that process, so we've gone through the development process, we've validated in the high pressure rig, I should have said at E-class conditions. And this summarizes where we've got to. So we started round about 2020 with our first testing in 2021. We've evolved the system to evolve the engine configurations or the engine features, coming up with the engine burner. And that burner has been, as I said, verified at E-class conditions. And we've taken it to the point where we've now evolved the design for a couple of applications, the Avon and the Frame 5. Okay? And also, the critical features within the burner are very suitable for wide ranges in Wobbe index as well as fuel reactivity. So that gives us an opening to not just natural gas and hydrogen, but other fuels as well. Okay. So much for a very brief overview of the development of the technology itself. As I stated, what we've then done is we've taken the technology and we've derived variants of it for the Frame 5 and the Avon. We've done that through our design rules that we've evolved through the testing and the analytics that we've done. And we've then verified it for operational and functionality within the combustor, including the issues related to metal temperatures, which are crucial for the system life. So a critical thing to note here, I've taken a certain technology, or we've taken a certain technology, we've then branched it off, the same knowledge, the same know-how, the same critical features, and applied them along a couple of different parallel paths. And again, in our future, we will also apply it to a number of other gas turbines as well. And focusing firstly on the Frame 5 product, this is what the upgrade that we propose comprises. So this is a model of our system within a Frame 5. And here you see the combustor casing of the Frame 5. And here you see our dry low emissions combustion solution with the burner. Now, when we integrate that within an existing Frame 5 diffusion system, for example, what we would change is the burner, of course, itself. The end cover here will also have to be changed because that's now suited for integrating the H2R burner. Another thing that will need to be done is because it's a dry low NOx premix system, we have to add an additional fuel stage. So here we have a pilot and a main compared to a single stage for a diffusion system. And so those are the modifications that would be made at the head end. We, of course, changed the combustor. Crucial to note is that it's a DLE combustor and already includes some features which are combustion dynamic mitigation features. Additionally, to enable our system to be integrated into the GT, we would also need to manufacture and procure new crossfire tubes which are able to be integrated with our combustion system. The combustor casing we will leave unchanged unless it requires it because maybe the existing system has had its useful life. In terms of the assembly of the system comprises two main assemblies. One is the liner assembly, which comprises the combustor liner and the cooling sleeve, and that would then go into the engine first. And at the head end, we have the head end assembly, which comprises the burner and the end cap, which then would be connected through to the various fuel lines at the back end here. So far as the auxiliaries are concerned, the auxiliaries and control system, again, if we are changing from a diffusion system to a DLE system, we do have to add a second fuel manifold to account for the pilot fuel. That in itself does need an additional control valve as well as manifolds. Crucial behind our system here is that, again, this has to be verified case by case, but certainly some studies we've done have shown we do not need to alter the fuel skid. We tee off the main fuel pipe here and take off a branch, which then fuels the pilot manifold. So far as the control and electrical systems are concerned, of course, we've got to modify to have now the pilot staging as also a control parameter as well as just the total fuel flow. We, of course, have to change the operating concept right from ignition through to baseload operation. And then, of course, there are the electrical changes that are required around, for example, bringing on the extra fuel supply and seeing to this additional control valve. In terms of then what that summarizes to in terms of offering is that it is DLE for natural gas. It is retrofittable. It has to be during a major combustor overhaul, but it is retrofittable in during an existing overhaul. There are no modifications to the gas turbine houses, enclosure, or cranage. The emissions that we offer then on natural gas is sub 15 ppm. We turn down to 65% load. These are the characteristics which are demonstrated on this chart on the right, which is then our expected emissions based on our high pressure testing, which shows then the NOx as we go down in relative load, and also the CO, which then eventually kicks off at around 60% load. And to summarize all of that, so far for the frame 5, we've got a DLE system which is sub 15 ppm. We've gone through quite extensive durability analysis to make sure we can achieve the targets that we've set. It's a drop-in combustor with minimal adaptations to the auxiliaries. And it is hydrogen ready. The combustor itself is hydrogen ready. And so when hydrogen becomes available to the plant, what people can start to fuel the system with hydrogen. And when operating on hydrogen, 100% hydrogen, we offer 25 ppm. That should be stated is at 15% O2 dry. With 100% hydrogen, there are also performance upgrade, or let's say performance gains, which comes through the change in exhaust gas composition, which again would be case dependent. So essentially, it's a low emissions retrofit for a frame 5, is H2 ready, and it's an asset life extension because it offers low emissions for the future. Turning attention now to the Avon. The Avon has been developed together with our business partner, Sulzer, and Crosstown has been responsible for developing the burner, and Sulzer responsible for developing the combustion system. A critical point to note is that this is an inline solution, which leads to no packet implications. So this can be retrofitted into an Avon without modifications of the system around the GT. Where things have progressed to is Sulzer has designed and tested the DLE combustor in an engine, though it must be said with a different DLE burner. So for our system, the Crosstown H2R / Sulzer system, we would then integrate our burner into the Sulzer combustor, and we expect that the combustor would remain more or less unchanged from today. In addition, again, same as the frame 5, we do need to make fuel system changes, but again, they are restricted to an additional fuel manifold for fueling the pilot with the control valve and the associated control and electrical upgrade. And this is again what now we offer for the Avon. It is a DLE for natural gas. Again, it's retrofittable during a major combustion overhaul. There are no modifications to the gas turbine enclosure or cranage, for example. It is 15%, 15 ppm on natural gas and turned down to 65% load, again, as demonstrated through this chart, which is our expectation based on our high pressure testing. And to summarize, we've got a DLE solution, which is sub 15 ppm on natural gas. Again, we've gone through extensive durability analysis to make sure it meets our targets. It's an inline solution for the Avon. And again, if hydrogen becomes available, the burner is 100% hydrogen ready, and one can exploit certain engine performance advantages when running on hydrogen. And again, this is a low emissions retrofit solution. This time for the Avon is hydrogen ready, and it's an asset life extension because it has low emissions which are in line with future regulations. For the product launch program, on the frame 5, we've already done some site-specific scoping. During the course of this year, 2025, we have still a number of slots available. So if people do want to get in touch, I urge you to do that we could undertake a site scoping to see what would need to be done for any frame 5 configuration, any particular frame 5 configuration, and that we would then follow up with a full feed study. So please do get in touch if you're interested. Our expectation is that the first installations would be from 2026. And as I stated, the burner is 100% hydrogen ready. As hydrogen starts to become more available, then it's open to the clients to push on to the 100% hydrogen in due course. So far as the Avon is concerned, I'm not going to say anything more than this one particular side, because that's something that we do need to approach together with clients, with our partner Sulzer. So again, Avon customers, if you want to get in touch, please do, and we can arrange a call with Crosstown and Sulzer. At that point, I'd like to close and invite people for questions.
Thank you. Thank you, Prith, and thank you, Khawar, for delivering such a very detailed presentation. So we are now going to open the question and answers session. At the same time, we are also going to open a Slido questionnaire on the quality of our webinars, where you can provide any feedback to improve our webinars for the future. So floor is open for any questions you may have. Please raise your hand and identify yourself. Thank you. Yes, Antonio, please go ahead.
Well, thank you very much, firstly, for the presentations. I might open the Q&A session today. I would like to know why you have decided to go for Frame 5. Is there has been any particular reason, or is it because you have got any type of support from the end users? Could you elaborate a bit more on that? And then, if there are other users who might want to introduce this technology into other engines, then what would be the process there as well?
So, first of all, I'd like to say we have received support from the Swiss government. They have a program similar to, I guess, the European Union program. So many thanks to them. Without whose help, we would not have been able to get this far. We received support from 2 end clients who may or may not be in the audience, and we've done the site scoping studies for them, which they have accepted. So I think that's very important that 2 clients with 2 quite different engines are happy with our product development for their particular engine. One is the Frame 5 machine, and the other one I'm not permitted to say what it is. We've had good support both from an engineering and technology side from our business partner Sulzer. So those are and we have actually done another large feasibility study for a company in California who was probably the very first one to approach us for our 85 megawatt gas turbine. So for these clients and for Sulzer's support and for the Swiss government support, we're very grateful. Right now, we're looking to do further site-specific assessments. These assessments will be focused at things like the field scale, the control system, the vintage of the control type, Speedtronics, or whatever the one is for the Avon, and to see how they need to be upgraded to be able to handle DLE technology and combustion physics. So scoping studies focused only on site-specific. We think the program we've gone through, which is a 4-year program for developing and testing the Combustion H2R burner, has been fairly rigorous, and we think we can bring that in to an engine in the near future, as we said, 2026. There are a few hands up. I'll let Nicola take the point, the whole person who's going to speak.
Thank you, Prith. So we have Simon Kidd. Please, Simon, floor is yours.
Hello, good afternoon. Simon Kidd from National Gas. I was wondering on the Avon how your DLE compares to the DLE that we have been developing with Alba/Sulzer. Is it complementary? Is it in competition? What is the commercial arrangement? And are there any limitations to the mark of Avon that it can be applied to?
Well, I can make a stab at it. I think some people from Sulzer may be in the audience, so I'd like them to come in on this, but let me start. The H2R burn is primarily developed to be a multi-fuel, multi-platform burner. It is not purely a DLE burner. So it is a DLE burner with full hydrogen capability. It can run on medium BTU and low BTU gases as well, providing they're within a certain range in terms of the fuel composition. And as we said, as Khawar said, we can put it in as purely a natural gas DLE solution. And then as hydrogen becomes available, you can maintain that in the machine. It is designed to fit into the current one that you've been developing at Sulzer. And I think it should be compatible. It's not in competition because in any case, we would go with Sulzer. Right now, we've configured it for the Avon 1553 for sure. That's what we've been asked to do by Sulzer. And based on the actual final combustion design that we match up to our burner, it may be capable of going into other Avon types. I think at this stage, I'd like to see if somebody from Sulzer who may be in the audience would like to say a few words. Does that answer your question, Simon?
It does, thank you. Is it possible to ask just one supplementary question? Is it possible to understand what you think the durability of your solution is in terms of the current overhaul life of an Avon is typically 30,000 hours? Do you see that being extended with this solution?
We can certainly meet the current overhaul period, and that was one of the specifications that we received from Sulzer. Amongst the others was start reliability, NOx, CO. All of those were defined by Sulzer, and that's how we used it to develop this burner. I see that Rainer Ludolf is in the audience, so perhaps Rainer from Sulzer, you could say a few words.
Yes, if you allow. Thanks a lot, Simon. Thanks a lot, Prith. I think pretty much everything's already been said. We're talking about an upgrade solution, Simon, with the capabilities which Prith has presented. Any specific details we would really take separately outside of that call with our partner, CPH2R.
Okay, thank you.
Thank you, Simon, and thank you, Rainer. We still have the floor open for any further questions you may have. Also, comments. Frank, please go ahead.
Yes, guys, thank you for the presentation. Very interesting. As you may know, Thomas and I have some similar product ongoing, but I'm curious on the, you can say or not, it's up to you, but on the commercial value of this product is reliable and for the future. That means, are you confident that you can produce this on the acceptable price for the customer? What is your view on that?
Our target is to be able to replace the combustion system for pretty much in terms of the, let's say, end user, similar to the current DLE systems provided by other OEMs and other aftermarket players. So we do not expect to be more. We might be the same or maybe around about the same value. So it is meant to be an economical solution. We did a customer survey and came up with a lot of different numbers which customers actually gave us in terms of what their expectations would be for such a retrofit. We're pricing it as a DLE solution only, but as you know, as we said, it can go all the way up to 100% hydrogen if and whenever the customer has that level of hydrogen to be used with this particular combustion burner. But just to give a bit of background, some of the engines we, Khawar, Franklin, and I have been involved with, and a couple of other gentlemen who are not here, have actually run with 40% hydrogen by volume for over 20 years in the field. And today, most of the engines that were developed by Alstom and now with Ansaldo are also capable of going up to high hydrogen content. So we are fairly confident that we can make a high hydrogen machine, a retrofit, keeping within the geometrical boundaries that the user currently has, and making an economical solution for the customer, as Khawar pointed out in one of the key needs. That was one of the key things. It has to be economical, it has to fit, and it has to run.
Thank you.
Thank you both. We still have some minutes to go. We can still keep the question and answers session open if you have any further input.
Yeah,
Antonio,
I might
please.
have one more question from my side to the team here. So can you elaborate a bit also more on how you ensure combustion stability across such a really big range of these fuel blends, especially when you are actually approaching to 100% hydrogen? And then another question would be, I understand that firstly you will need to start with natural gas and then you do the switch, or how, if you can elaborate on that?
Yeah, sure, Antonio. So essentially, when one's going from 0 to 100% hydrogen, we're able to do that really over a wide load range. So it isn't so much as a switch, it's bringing on the hydrogen as required. It does certainly bring challenges for stability. I alluded to during the presentation that we are very focused also on combustion dynamics, which will change quite dramatically as one goes from compact hydrogen flames to more diffuse natural gas or lower Wobbe index fuels as well. That's crucial to do, but that's been quite an effort within our development to tackle that. So far as the 100% hydrogen is concerned, that's more of a burner type of characteristic. So one has ensured that we are well away from flashback margins. So far as flame stability is concerned, that is then more of an integration between the burner and the combustor itself. So that's an integration issue that we also, again, now focus a lot on for the Frame 5 and the Avon as part of that integration.
And just to reinforce that, if anybody is interested to have, I mean, this is very open discussion, so we cannot reveal everything that we've done, everything we've targeted on this approach. So if anybody is happy to, I mean, if anybody wants to talk to us, feel free to contact us. I mean, the coordinates are with Niccolo and with Antonio, and we can just get in touch with them and they'll put you in touch with us, and we can carry out a more detailed conversation, especially where we've actually done on-site reconnaissance and measurements, let's say for frame 5 and the very large machine, we can certainly look at that together with on a one-to-one basis with the client. And if it's an Avon client, please get in touch with us. We will integrate that together with Sulzer, and then we can have a, let's say, more factual, on the hardware type of discussion as we go forward.
Thank you, Prith. Indeed, if you have any further questions you would like to ask to Crosstown, you can also reach ETN bilaterally, and then we'll be happy to help you out and contact Crosstown to follow up on a separate manner. We do not see any further questions or comments, nor in the chat. So we would propose to close the webinar now. Please be aware we are going to upload the presentation in PDF format on the ETN Global website. We are also going to upload the recording of today's webinar on the ETN YouTube channel. Lastly, we would like to thank again Prith, Khawar, and also Franklin for their commitment and their availability to present at today's webinar. And also would like to thank you all for attending today's webinar. And we look forward to seeing you online at future ETN events, either inline or in person. Thank you very much.